Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 8, Projectivities in One-Dimensional Forms. Section 81, Scale on a Conic. The notions of a point algebra and a scale, which we have developed hitherto only for the elements of one-dimensional primitive forms, may also be studied to advantage on a conic. The constructions for the sum and the product of 2 points, numbers, on a conic are remarkably simple. As in the case on the line, let 0, 1, infinity be any 3 arbitrary distinct points on a conic, c squared. Regarding these as the fundamental points of our scale on the conic, the sum and the product of any 2 points x, y on the conic which are distinct from infinity are defined as follows. Definition: the conjugate of 0 in the involution on the conic having infinity for a double point and x, y for a conjugate pair is called the sum of the 2 points x, y and is denoted by x plus y, figure 94 left. The conjugate of 1 in the involution determined on the conic by the conjugate pairs 0, infinity, and x, y is called the product of the points x, y and is denoted by x dot y. Figure 94 right. It will be noted that under assumption P, this definition is entirely equivalent to the definitions of the sum and product of 2 points on a line, previously given Chapter 6. To construct the point x plus y on the conic, figure 94, we need only determine the center of the involution in question as the intersection of the tangent at infinity with the line joining the points x, y. The point x plus y is then determined as the intersection with the conic of the line joining the center to the point 0. Similarly, to obtain the product of the points x, y, we determine the center of the involution as the intersection of the lines 0, infinity, and x, y. The point x dot y is then the intersection with the conic of the line joining this center to the point 1. The inverse operations, subtraction and division, lead to equally simple constructions. Since the scale thus defined is obviously projective with the scale on a line, it is not necessary to derive again the fundamental properties of addition and subtraction, multiplication and division. It is clear from this consideration that the points of a conic form a field with reference to the operations just defined. This fact will be found of use in the analytic treatment of conics. At this point, we will make use of it to discuss the existence of the square root of a number in the field of points. It is clear from the preceding discussion that if a number x satisfies the equation x squared equals a, the tangent to the conic at the point x must pass through the intersection of the lines 0, infinity, and 1a, figure 95. A number a will therefore have a square root in the field if and only if a tangent can be drawn to the conic from the intersection of the lines 0, infinity, and 1a. And conversely, if the number a has a square root in the field, a tangent can be drawn to the conic from this point of intersection. It follows at once that if a number a has a square root x, it also has another, which is obtained by drawing the second tangent to the conic from the point of intersection of the lines 0, infinity, and 1a. Since this tangent meets the conic in a point, which is the harmonic conjugate of x with respect to 0, infinity, it follows that this second square root is negative x. It follows also from this construction that the point 1 has the square roots 1 and negative 1 in any field in which 1 and negative 1 are distinct, i.e., whenever H0 is satisfied. We may use these considerations to derive the following theorem, which will be used later. Theorem 24. If AA prime, BB prime are any 2 distinct pairs of an involution, there exists one and only one pair, CC prime, distinct from BB prime, such that the cross ratios R of AA prime, comma, BB prime, and R of AA prime, comma, CC prime are equal. Proof: let the involution be taken on a conic, and let the pairs AA prime and BB prime be represented by the points 0, infinity, and 1a, respectively. Figure 96. Let XX prime be any other pair of the involution. We then have, clearly from the above, XX prime equal to A. Further, the cross ratios in question give R of 0, infinity, comma, 1a equal to 1 divided by A. R of 0, infinity, comma, XX prime equal X divided by X prime. These are equal if and only if X prime is equal to AX, or if XX prime is equal to AX squared. But this implies the relation A equal to AX squared, and since we have A not equal to 0, this gives X squared equal to 1. The only pair of the involution satisfying the conditions of the theorem is therefore the pair C prime equal to -1, -a. Exercises. 1. Show that an involution which has two harmonic conjugate pairs has double points if and only if -1 has a square root in the field. 2. Show that any involution may be represented by the equation x prime x equal to a. 3. The equation of exercise 13, page 230, is the condition that the lines joining the three pairs of points AA prime, BB prime, CC prime on a conic are concurrent. 4. Show that if the involution x prime x equal to A has a conjugate pair BB prime such that the cross ratio R of 0, infinity, comma, BB prime has the value lambda. The number A lambda has a square root in the field.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.